Hello? Hello? Let me know if you can see me or hear me. You guys can see and hear? Hello? Testing? I had some problems this morning, so. Amen and hallelujah. Looks like we're back. Fantastic. Hi, everyone. I do not have children, but like many other professors, I have animals. So if they, and I have a husband who's not working right now. So if you guys hear Brandon making lunch, which he's doing right now, or dogs clicking around, I'm doing the best I can. So, hi everyone. Welcome to Organic Chemistry, Part 2, the online edition. We've got it's been a weird 2 weeks, right? It's been a very, very weird 2 weeks. So we're doing the best that we can though. Couple quick things to note. There is somewhere about a minute or so delay between when I say something and you see it. And you can be on 2 different computers in the same room as someone and get them at slightly different times. I think it depends on the computer and the connection and all kinds of factors that, I'll be honest, I don't fully understand. But that's what we got. So this is what we're working with. So a couple of you came by and got model kits earlier. Yay! We're going to be using these quite a bit for the next couple of days. So if you find that you still need them, I have brought a bunch home with me. So just let me know and you can come by and I can get them for you if you realize that you still need them. I know not everybody was available today. And it was very cold out, so I didn't want to sit outside longer than I had to. So also, sorry, I will be taking pictures, I guess, of everybody's exams and sending them out. It might take a while because that's kind of a slow process, but my apologies for leaving those at home today. Some of you have asked how to do the exams, and I'm not exactly 100% positive how that would work. When we had the great flood of 2010, I wasn't teaching organic then, I was just teaching biochemistry. But what we had that semester is I did kind of take home exams. So what I can do is essentially put them on D2L, and you don't even have to like, I'll make them so you can just write, hold it up on your screen and just write on paper and take pictures and send it to me. And so it'll be a timed exam. You can send them to me when you are finished with it within that time frame. And that should work pretty well for us, I think. We'll have a few different time options because I know some of you are going to have kind of unusual time commitments compared to normal. So there'll be a couple different versions of the exams. So that way, you guys can be a little bit more confident that, your classmates aren't cheating off each other, hopefully. I would hope you guys wouldn't do that anyway, but experience has bit me in the butt on that. So, okay, I have to do it. I got a new keyboard and it has a plastic thing on it. I can't have that there. I'll just want to pick at it the whole time. Oh gosh, now it's stuck to me. All right, have your hand sanitizer. We can do this. All right, so the first thing that I want to do is swap over to Sketch. And what I want to do is turn off my phone so I don't keep getting alerts. And I would like to, I'm also working with a new writing pad, so I'm kind of getting the hang out of that. instead of writing on my screen, because I can write on my screen, but you'll notice it moves the camera, which is kind of annoying. So I got a writing pad for it. So what I wanted to do is start off our conversation today talking about stereochemistry. So we've learned about different types of isomerism in class, and we usually draw like a little triangle or like a pyramid, and I'll do that here in a minute also. I would encourage you to take notes on what I'm doing here, just like what we would normally do in class. I think that'll probably be most effective. And by all means, email me or whatever if you have any questions on what I'm doing. Quincy, how's everyone doing? We're in quarantine, Quincy. That's how we're doing. So anyway, what I want to start off with, though, is a simple molecule. So I want you to think of a carbon with 4 different things attached to it. That is really tiny. Let me make that bigger. Also, FYI, I have about 8 screens open whenever I do this, and so if it takes me a minute to switch back and forth, you're going to kind of notice that. Okay, so here I have a carbon with 4 bonds, and on that, let's see, what did I put together here? So I have a model. One of these is a nitrogen, so slap on a nitrogen. One of them is an oxygen. One is a chlorine, and one is a hydrogen. So if I asked you to make this model, there's, I don't know, maybe a solid chance that some of you would make this version and some of you would make this version. And I know that when you're not next to me, it's kind of hard to tell what those versions are, okay? But what I'm going to be working with today is the molecule that you have on your screen. So if you want to make 2 of them, and then I'll show you how to make sure we have the 2 different options, and then we can kind of get started for today, all right? This conversation is going to probably take a little bit longer than it normally does. So that's just because of the barrier, obviously, that we're kind of dealing with here. So make the molecule, and then let me switch back over to paint. All right. So one of the things that we've seen kind of over and over again, there we go, is we kind of have this multiple tiered idea of what isomers are. And so and I know you've seen me draw this like 1,000 times, but there's a reason. Okay. So one of these is a constitutional isomer. And we talked about constitutional isomers as being, I don't know if I can use superscripts and subscripts on here. I can, okay. So a constitutional isomer would be something like ethanol versus a molecule called dimethyl ether, which we've seen that example used a few times in class so far, so that shouldn't be a new one for you. There we go. Then we have the conformational isomers. And for those, we had the rotational isomer. My dog's being special. We had the rotational isomers, like the anti versus eclipsed, We also had the chair conformers. So those were kind of different versions of the conformational isomers. They were differing in their energy levels. There we go. And then in this arm over here, we haven't spent a whole lot of time talking about it yet, but we have what are called stereoisomers. And we have a couple different types of stereoisomers. So the first one that we talked about already a little bit, and we're going to talk about it more, are called diastereomers. And then I'm kind of running out of space here, so let me do it this way. Your paper, you probably have more room to write this than I do. Okay. So the one that we're going to be talking about today are called enantiomers. That's pretty much, after we get done with that, that's like 90% of our conversation on isomers. We'll only have really one type left of diastereomers to talk about. So far with the diastereomers, we had talked about cis-trans isomers as being diastereomers, right? And so our conversation of enantiomers is going to be a little bit different. So what I'm going to have here that you can write down in your table, and then I'll talk more about what these things mean, is there's RS isomers, enantiomers. There's plus minus. There's big L, big D, and there's little l and little d. Okay? They're all the same thing. So I'll go ahead and keep that up on the screen for a little bit so you guys can write those down if you want, which you should. But what I want to give you, and I always start off this lecture talking about a little bit of history. So right now what I want is, if you have model kits, make the molecule. I have a green, a red, a blue, and a white. Okay? Make that, and then have this table so we can kind of talk about it, okay? So back in the mid-1800s, there was a French scientist, Louis Pasteur, and he was really famous. You've probably heard of him for various things, not just what I'm talking about today, but in a kind of hilariously stereotypical manner, he was a French man studying wine. And there was a chemical in the wine, tartric acid. And he started looking at the tartric acid and trying to kind of improve wine quality. Okay. And so what he did was he started looking at the solid crystals of the tartric acid that I guess were kind of crystallizing out of wine and giving it a weird flavor. I don't drink wine, so I'm not exactly positive how this worked out for him, but it's one of these things he did in the process of studying this wine. And he noticed that underneath a microscope, it looked like there were two different types of crystal shapes. So if you think about the like giant geodes and things like that, they have a very defined kind of crystal structure. And so the tartric acid had two structures. And that was kind of the first time that people had looked at them like that. And I mean, it was literally like 1849 or something, right? This was a really long time ago. So he started doing more research on this. And one of the things that he decided to try and do, don't know where he got this idea, but he decided to try and take light that was polarized through a plane, so plane polarized light. So normally if you have a light source like a light bulb, you'll have light waves coming from every direction. Plane polarized light means you've basically shot the beams through a slit so that all of the beams that come out the other side are all going in one direction. So he did this with the tartaric acid crystals and noticed that the molecules would rotate, the crystals would rotate plane polarized light. The ones that looked one direction would rotate it one way, and the ones that looked the other way, or that looked the opposite, would rotate it the opposite. And so that's when we kind of got this idea that you could have one molecule that looks exactly the same but might actually have two different forms to it, like cis or trans or things like that. The enantiomers are going to be a more subtle difference than what we're used to seeing with cis and trans, right? With cis and trans, it was very easy. They were same side, opposite sides. That was it. And those were very, very easy to look at. The constitutional isomers are very easy to notice and to look at. The chair conformations, you guys did pretty well with that. Actually, it's been 2 weeks, so it's been a long time, but I want to mention that you guys did better on your exam than I've ever had any class do, so I don't think the exam was too easy. I think y'all are just awesome, so keep up the good work. But so basically, it became obvious that there were two different ways of having a molecule like this. So what I'm going to do is I'm going to go back to a big web screen so you can see it a little bit closer. Here, and you guys have to forgive me, so I'm like looking at myself, but everything's backwards, so it makes it kind of hard to finagle things. I'm going to hold the green one here and hold the green one here. Oh, that worked out well. If you notice that I'm holding things that look exactly the same, like they're looking at each other in a mirror. Okay. Now, if I rotate that, and you can look at it, it still looks like you can tell that it goes white to blue to red in one direction and white to blue to red in the other direction. If I try and overlap these, you can see that the greens that I'm still holding on to here and the blues overlap, but the white and the reds don't. So the white and the red are off. If I wanted to try and align it and rotate it so the white and the red are the same. So now I'm holding the red ones. Now you'll notice the blue and the green ones are staggered. The easiest way to see this is if you make these two models yourselves. Okay? So the easiest way to do it is to make one of them and then make something else that looks like the mirror image of what you would be expecting to see. Okay. So I'm going to stop for a second. So I just pulled up my chat window. So sorry, I'd had that closed while I had the big screen up. Do you guys see what I'm talking about here? So I'll make it so the white's pointing up. The blues are behind, the greens are out front, and the reds are to the side. I can scale it a little bit there so you can see it. But these are not the same molecule. These are the two types of things that Pasteur saw in the wine. Okay. Any questions so far? I told you there's about a minute delay, so. Everybody's answering yes. I don't remember what I asked. Did I just say, is everything making sense so far? If that's what I asked, then that's, one is clockwise, one is counterclockwise. That's a great way of looking at it. I don't know who that was. Yeah, they're exactly mirror images of each other, Lorena. So I'm going to set that down for a second, and I'm going to go back to my, I guess it helps if I do this too. So the definition of an enantiomer, okay, so we have our definitions of like constitutional isomers. A good definition for that would be like molecules with the same formula but different connectivity. I think I've actually used that exact phrasing before. For the conformational, they had differences in energy levels, right? Depending on how much steric strain they had, depending on how they'd been aligned and things like that. The diastereomers were molecules that, how about this? I'm not going to define that one yet, because when we learn the other one, it's going to make more sense with this. But so far we can think of the diastereomers as having cis and trans options, right? And those are very easy to see. They also have different levels of energy for the cis and the trans. With enantiomers, there's a very specific definition that gets used a lot with that. So these are non-superimposable mirror images. There we go. So when Lorena said they're basically mirror images, that is the exact definition of an enantiomer, is they are non-superimposable mirror images. So you could have an image of anything, right? So if I were to take water and another water, you can see, oh, these are mirror images of each other, but they're superimposable. I can lay them on top of each other and they're exactly the same. So not enantiomers. Those would be superimposable mirror images, which would be things like methane, anything like that. So the definition of enantiomer is very specific. It's non-superimposable mirror images, okay? So what's important is that everyone can see that these are two different forms of the same thing, okay? So on this one, you'll see the green is pointing one way. This one, the green's pointing the other way. I told you, everything's inverted in the camera. It's kind of weird. Superimposable means that it can be laid on top of itself. Benny, I'm sorry. That might be a connection issue. But so superimposable means you can lay them on top of each other. So a good example of this is your hands. So your hands are non-superimposable mirror images of each other. So they're mirror images of each other, you know, provided you have symmetric hands. I did have somebody one year who had, she was missing 3 fingers, so her hands were not mirror images of each other. But for most people, that's what they look like. But they can't be laid on top of each other and be the same, because you're always going to have your thumbs out, right? Your middle fingers are the only thing that would be overlapping. So, Vinny, we might need to get you a connection. Sorry, Bubba. Okay, so Lorena, I hope that makes sense when I say what does superimposable mean. Now, there are a couple things to note, and this is, I'll just talk about this before I get into the RS, LD, and all that kind of thing. These are non-superimposable mirror images that only differ in how they rotate plane polarized light, not plane. And I'll just say and biochemistry. So, for example, your entire body has very specific enantiomers of things like sugars, amino acids, all of that stuff have enantiomers. And one type, so the R versus the S or the L versus the D, is what your body uses. Can't use anything else. So they differ in how they rotate plane polarized light. One will go one way, one will go the other way. But they also are different in how they react in a biochemical system. Okay. So I'll just write down they're different in biochemistry, they're different how they rotate plane polarized light, but that's pretty much the only difference. Okay. So with that said, I need to go over a few words. So I don't tend to do a whole lot of just kind of definitions and things, but here we go. Number one. You know, I need to make my writing here smaller. Because otherwise, I'm just not going to have room for anything. I can still see that. I think you guys can still see that too. Alrighty. So, you know, I kind of wanted you to have your graph or whatever, your table, or your pyramid of your enantiomers and all the different types of isomers, basically. But so I also want you to just have kind of a list of words and what those words mean. So enantiomers are molecules that have two forms, and those forms are non-superimposable images of each other. Okay. Enantiomers are what is called chiral. So chiral is not necessarily a chemistry word. Like eclipsed is not necessarily a chemistry word, right? That can just mean like an eclipse of the sun and the moon, right? But when we're talking about it, you're pretty much never going to hear it outside of chemistry. That's kind of how chiral is. Chiral is something that has non-superimposable mirror images. So your hands are not enantiomers because it's not a molecule with two forms, but they are chiral. And enantiomers are chiral. So that's just kind of a word that goes along with this conversation. You can refer to molecules as being chiral. You can refer to specific enantiomers, or you can call them enantiomers. Okay, so there's kind of some terminology that's new that you have to learn. I don't have a fast or easy way to do that. It's just kind of, you have to memorize the words, which I hate doing, but that's just kind of the way we have to do it regardless of whether we're meeting in person or online. Okay, so chiral and enantiomers. Racemic. Let me see if I can like spell that phonetically. Racemic. I'm not great at spelling things phonetically, but I think that'll help. It's kind of a weird looking word. It's not pronounced exactly how it looks. So racemic is where you have both types of enantiomers together. So that's generally what you have if you were to do most syntheses. Like, I made this molecule. Well, a lot of times if you make it, you make both. It's very hard to make just one, and that's a whole area of chemistry that you learn in graduate school that we're not going to cover a whole lot of in this class specifically. Okay, you'll see a little bit about it in organic too, hopefully face to face. But you'll definitely see it if you ever go on to graduate school and learn graduate level organic chemistry. You'll learn about all these fun reactions that just make one of the two molecules. There's enantiomeric excess. There we go. An enantiomeric excess is when you have more of one than the other. So you might have, let's just call this R and S. You might have 60% R and 40% S. So you would have an enantiomeric excess of R because you had 60% versus 40. That's useful because some reactions give you more quantity of one than the other, and so you can talk about that using that phrasing, enantiomeric excess. There was another one. A stereoselective reaction makes one enantiomer specifically. So it makes one stereoisomer. You could also use stereoselective when you're talking about the cis-trans diastereomers. If you were to do a reaction where you made one versus the other, you could also use that phrasing for that. Okay. So those are the majority of the words that I need us to kind of think about and know. I will be using those words, especially enantiomers, chiral, racemic. Those will get used a lot. And so I need you to kind of know what those mean, even if you have to like stick little flashcards or like sticky notes on the sides of your computer screen so you know what I'm saying when I use those words. Whatever it works, do it, okay? All right. So now I want to get back into that RSLD plus minus thing. Okay. So back when Pasteur was studying his wine and his tartric acid, and he came up with that discovery that there's actually two forms of certain crystals. Normally, I actually show on the overhead, Miss Donna in her office, the chemistry secretary, she's got this giant like geode, and you can actually see the different large crystals of that and how some of them look like the opposite mirror images of another. If you Google geodes and things like that, you might be able to see what I'm talking about. But when he was hitting these with plane polarized light, and they would move the light, the plane of light was this direction, and then it would go either this way or this way, right? That's what was happening. So I'm just going to write plane polarized light is technically hyphenated, I believe, but that didn't happen here. So what happens in plane polarized light? If it moves it to the left, that's my left, but I guess it's your right. So, okay, so if it moves it to the left, that was called levorotatory, meaning rotating left, levo, left. And that was given two types of kind of terminology. So there was a little L, or rotating it, basically thinking of that as like an axis. If you're rotating it this way, you're rotating it to the negative direction. So the other way of kind of indicating that was with a negative sign. If you did it to the right, it was dextrorotatory and was indicated by a little letter D or a positive sign because it was rotating it in the positive direction. Okay. So I'm missing like an indent bracket there, I'm sorry. So in the very, very early days, that's all they knew. They knew that if you stuck a crystal that looked one way, they didn't know that the molecule looked like this. All they could see was a crystal because this was like the 1800s, right? They knew that if you stuck it in that plain polarized light, one would do this, one would do this. That's all they knew. So they put some of them as a positive, some of them as a negative. Alternatively, they could say it was levorotatory or dextrorotatory. Okay. Now, if you go to, I'm trying to think of a good dietary supplement that people take. Lysine. So there is some research that lysine helps with, I don't remember if it's, I think it's with cold sores. Just give me a second and I'll show you what I'm talking about. Copy, paste, copy, paste, copy, paste, copy, paste. All right. So to this day, you can still find various dietary supplements that have this type of terminology on them, where it'll have a D or an L. Sometimes you'll find it with a plus or a minus. Okay. That's because the dietary supplements are biomolecules. So lysine is actually an amino acid. And biochemists still use this LD system and the plus minus system. I can't really explain why. Do you need my keys? Sorry. Second. Yeah, that's fine. Okay. Bye. Be safe. Do you need sanitizer?
I lost mine.
Hand sanitizer. Okay. So you'll notice that on this picture specifically, there's a big L, not a little L like I just showed you. So there's some history with that also. The old days, they didn't know which molecule was the D and which one was the L. They knew that they knew that there were two forms that looked like this, but they couldn't identify which one was which. We just didn't have the technology. So in the very, very old days, they used to use a system where they basically used a molecule called glyceraldehyde. So glyceraldehyde, like the name says, has an aldehyde on it. I have to write kind of slow to make sure it's super legible here. Okay, so that's glyceraldehyde, and this is one of those molecules that have the R and or the L and the D forms. So what was done is they just used glyceraldehyde as a standard for everything. And they said the one that's L, we're just going to assume it looks like this, and everything else that looks like that, we're going to assume looks like that. And we'll call that big L. And the one that we're assigning D, that we say looks like this, everything that looks like that is going to be D. Okay. They had a 50-50 chance of getting it right because you're talking about two forms. It turned out that they actually picked the right one. We found it out like in the 1950s. So, what that means though is that the old system is something we call relative stereochemistry. Because it's relative to the structure of glyceraldehyde. The new system is called absolute stereochemistry because we know the real structures now. Okay. So if you were looking at this, and let me pull up my chat window in case anybody's asking about it. Okay. So if you are currently a little bit confused on this and you say, how do I know which one's L and which one's D? How do I know which one was the plus minus glyceraldehyde? You don't need to know. I give you the history on this because I think it's kind of interesting. It shows progression on what we knew versus what we didn't know and how we've adapted over time to kind of incorporate new definitions. I also tell you about relative stereochemistry because the vast majority of you are planning on taking biochemistry at some point. So you will see the L and the D used in biochemistry exclusively. They do not use the new system, which uses R and S. Okay. So if we want to, the old system uses a big L and a big D. The new system uses an R and an S. Okay. I'm trying to be consistent here, and it's just not working at all for me. Oh, come on. I don't want to save anything. I'm leaving it. Okay. So far, I need you to know what an enantiomer is. I don't need you to know how to find the two differences yet. I need you to know what the word chiral means. And then racemic and enantiomeric excess stereoselective reactions, we can kind of catch those as we go. I need you to know that there are more than one way that this type of stereochemistry has been notated in the history of chemistry since the 1850s, since we've known about it. There's plus minuses, which were the same thing as an little L or a little D. And then there was the old system that was relative stereochemistry, relative to glyceraldehyde, that used a big D and a big L. And then and that still gets seen on dietary supplements. Sometimes you'll even see the plus and minus signage as well. And then now we use a new system, which is the only thing we will focus on in this class, which is the RS system. So are there any questions right now about what you need to know and what's going on? Take a sip of tea. So racemic, what about it? That's right. So far, the only thing that I need you to know for the rest of our conversation for the next few days is chiral and enantiomer. Okay, you can read about all of these words in your book, And I think that I know that a lot of you don't read in the book because you prefer to hear it from me, or you don't know how to read. No, I don't think that's the case. Um, but I think that with this situation that we have going on right now, it's going to be really important for you guys to read your text along with attending my online lectures. So, okay. So that's what I needed you to know right now. And with that, we can do the next few minutes of the first step, which is finding a chiral carbon. Okay. So let me scroll down a little bit. Okay. How do we find a chiral molecule? There are a few things that you can look for here. I'm doing this in paint so I can draw the molecules along with it, but I don't think it does bullet points. So just act like I'm making bullet points instead of little asterisks. Okay, so you can find a chiral molecule by finding chiral atoms and looking for symmetry. Okay. So if you have a chiral molecule, that means there's two enantiomers, right? The R and the S form. Don't need to know how to find the R's and the S's yet. I just need you to know that there's two forms. I need you guys to understand how to find a chiral atom first. Okay, so that's what our first lesson is for this. So a very general rule, and this is something that if you have trouble with the structural aspect in your brain, which some people do, you can basically learn these by a checklist. I mean, you could essentially do it that way. So what I need you to look for when you're looking for chiral atoms, look for a tetrahedral atom. Okay, so that means we're talking about something that is sp3 hybridized. Okay, I told you we would be continuing to talk about that this semester. So look for a tetrahedral atom, something that's sp3 hybridized, connected to 4 different things. That's it. So there's a reason I used 4 different colored atoms for this. It is a tetrahedral atom, my carbon, bound to 4 different things: blue, red, white, and green, or whichever color you feel like using on your models, because I know some of you have your own model kits. If you have a tetrahedral atom connected to 4 different things, you have a chiral molecule. That's it. That's the definition. Okay. Now, when I say attached to 4 different things, that can be hard for people because you've not really seen things in terms of things connected to other things. Okay. So what I need to do is do a select. So, okay, this will be easiest to do if we do full structures instead of skeletal structures at first, but we'll get to the point where the skeletal structures will be pretty easy too. Okay, so if I have a carbon attached to a hydrogen, let's just put another carbon there. Okay. So let's look at this molecule that I have drawn here. It would be a hydroxypropanoic acid. You wouldn't know how to name this one yet. So to find our chiral atoms, we have to look for tetrahedral atoms that have 4 different things connected, okay? So let me change my color here. So this oxygen right here that I'm kind of circling, don't know if you can see that, it is indeed tetrahedral, right? But it's not connected to 4 different things. It's connected to a hydrogen, a carbon, and 2 lone pair. 2 lone pair are 2 of the same things. Can't be chiral. The carbon next to it is sp2 hybridized, so it can't be chiral either. Same with the oxygen on top of the carbon-oxygen double bond. The carbon on the far side, that I'm going to highlight here, is tetrahedral. So can an atom be chiral if it is connected to the same atom? It can, Quincy, as long as the that atom is connected to others. I'll show you. So this carbon here that I did with the blue has 3 different hydrogens on it. Okay, that can't be chiral. It needs 4 different things attached to that atom. The carbon here in the middle that I'm putting in red is attached to a hydrogen. That's one thing. It is attached to a CH3 group, which is a second thing. It's attached to an alcohol. That's a third thing. And it is attached to a carboxylic acid. That's a 4th thing. So 4 different things. Now, Quincy said, can an atom be chiral if it's connected to the same atom? Well, this, maybe I don't understand your question, but this carbon is connected to 2 other carbons. Okay, so yeah, it can be connected to the same atom as long as those atoms have different things. This one has 3 hydrogens. That one has 2 oxygens and a hydrogen. Okay. And Quincy, if I didn't understand your question, please let me know. Okay. So the way that we actually notate a chiral carbon is by putting an asterisk next to it. That means that it is chiral. Okay. That is not a Dr. Mann notation. That's a standard notation that gets used. So let me do another one. So let's look at something like all right. 2-bromopropane, or I don't think I've ever heard anybody call it like isobromopropane. Maybe isopropyl bromide. Some people might call it that. Okay, good, Quincy. So in this example, if I look at, how did I do that coloring? If I look at this carbon that I'm highlighting, yes, it is tetrahedral. It is connected to 3 different three hydrogens, which are all the same thing, right? So it can't be chiral. It's the one here on the far right. 3 hydrogens can't be chiral. The one in the middle, however, I want you to look at this one carefully. It's connected to a bromine, 1, a hydrogen, 2, a methyl group, 3, and then another methyl group, 3. Can't be chiral. Yeah. So I mentioned down here that you can look for symmetry. Yeah, it's connected to two CH3s. So there is, oh, let me see. There is a plane of symmetry that runs down the middle of this molecule. If the plane of symmetry is there and there's something that's exactly the same on either side, it can't be chiral. It means you got two of the same thing on either side. Okay? So let me do another one. And I'm going to do it with the more like skeleton notation. Or skeletal notation. That's ugly. Try it again. Okay. So if I just took hexane, how it is, there's a CH3, CH2, 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 CH3, right? You can't have any of those be chiral because all of them are connected to at least two hydrogens. If you have two hydrogens, you can't have four different things. So hexane is what would be called achiral, meaning not chiral. However, if I put something on one of my carbons here, let's say an OH group, okay? Now, at this carbon specifically, I have a hydrogen, an oxygen, an OH, a CH3 group. Let me just do this way. And then this whole mess of stuff. So that would make this carbon chiral, the one there in the middle of all that. Okay. So you're really just looking for planes of symmetry, right? If I wanted to do one that gets people a little bit confused sometimes, let's look at a ring. So let's say I have cyclohexane. Cyclohexane is made up exclusively of CH2 groups, right? Connected to each other in a ring. So it can't be chiral. They're all tetrahedral, but they all have at least two hydrogens on them, so they all have the same thing, right? If I put a fluorine on here, this molecule is still achiral, okay? Because I have a fluorine and a hydrogen, so essentially you're looking at this molecule here and having to remember that you're looking for lack of symmetry to be chiral. Well, here's, you know, everything on one side, here's everything on the other side, same stuff. Okay? So that molecule would be achiral as well. Now, let me show you what would happen if I change that a little bit. So instead of having just a fluorine on there, now I have a fluorine with a double bond in there, not on the fluorine. So if I put it with the fluorine, that would cause problems because it would no longer be a tetrahedral carbon. But now there's no symmetry in this molecule. Okay. If I were to draw and kind of dump that same line down the middle, we can see that this group here with the double bond is different than this group here with the single bonds, okay? So this molecule would be chiral because what's going on here? That carbon, there we go, is chiral. This pen has buttons on the side, and I keep hitting them. And I think it's because they very much structured this for a right-handed person, which you might have noticed. I am not. Oh, wait, I don't need that plugged in. Well, hot damn, look at that. It's wireless. things we learn. All right. Doesn't this run during normal class time? Katie, what are you talking about? Yes, we're during normal class time. Is that okay? Anyway, what I was going to say is it is 2:25. Okay, so the way that I'd kind of perceived this going down, because it is a little harder to ask questions this way, obviously, is to say, if you have questions, ask them. I will be on for at least, 10 more minutes, or if nobody has questions, I'll just log off. But I wanted to have extra time to ask questions kind of at the end of my lecturing. So if you have questions, you can ask them. If you are more interested in asking via the phone, you can definitely just like take a picture of what you're trying to do and send it to me, or you can email me or anything like that. Okay. So other than that, I'll just keep seeing you guys every Monday, Wednesday, Friday at 1:25. I have us scheduled until 2:25 every Monday, Wednesday, Friday, just because it does take a little bit longer to get stuff. You can come and go as you need, obviously. So if you have any questions about how the format's set up or anything like that, feel free to ask me. If you need clarification on anything that I talked about, please ask me. We'll do a couple more examples of this on Wednesday. The lab time is not going to be live. Okay, I'm going to have my husband come in and help me. Yes, this is chapter 5, Emily. I'll have my husband come in and help me record a couple things to give you guys, and I'll just post that as a video on YouTube for those of you who are in my lab. I think Dr. P's doing the same type of thing, or maybe just giving you guys data. I'm not exactly sure. But that's it, I guess. We out of time. So if you have more questions, though, I'm here. I'm not with you. I miss your faces. But I hope that this worked pretty well for you. I don't know. Vinny sounded like he might be having trouble with his internet connection, being a little skitsy. I don't know. Let me see if anybody's emailed me from class trying to get help with anything. Okay. So this might be a stupid question, but if you were to draw the symmetry line down another carbon, would that mean we're trying to find if that carbon is chiral? So the first thing that you would want to do is see if that carbon has 4 different things attached to it. So like this one here, oops, sorry, I have my wrong screen up. So this one here, this carbon has 2 hydrogens on it. So even if I draw a line down, it's not symmetric on each side, but it doesn't matter because it doesn't meet that standard criteria that it has to have 4 different things attached to it. Joanna, is there anything we should look over before Wednesday's lecture? It would be great, and that's a wonderful question. Thank you for asking. It would be great if you guys could do some problems in your book that look like what we just did here. That would be fantastic. After getting down what these chiral carbons are, like finding chiral carbons and identifying them, then we're going to start looking at designating them R or S. So if you want to, you can start by looking at what are called the oh, I spelled that wrong. Ingold Prelog rules. That's it. So, no, I think it's K-A-H-N. I think I had it right the first time. It doesn't look right that way. K-A-H-N, Ingold Prelog rules. We'll act like that's an A, and that's going to be an H now. Looks terrible. Lorena, did I answer your question? Hopefully it made sense. Come and join me for tea every... Good, Lorena. Come and join me for tea every Monday, Wednesday, Friday remotely. Oh no, I'm out of tea. All right. Well, if there are no more questions, I guess I'll just log off and see y'all on Wednesday. See you. You can see me, I guess, but I can't see you. I know some of you were using Zoom. If you prefer Zoom, the way that that works, let me know. I've just used this one a lot, so I'm most familiar with it, but it's up to you. I'm glad you think so. Oh gosh, my nose itches.